Hello there, thanks for tuning in, and I hope you're doing well. This video will deal with the topic of solving trig equations, and I would like to illustrate some of the differences between solving a trigonometric equation and solving a regular old algebra equation where you're just trying to find the value of the variable. I will use several examples to do this, and all of the solutions in this video will come from the unit circle. Okay, so just to say that at first. So let's our first example there, 2 sine x minus 1 equals 0. All right, now one of the main things that's different about a trig equation is that instead of isolating x at first, you have to isolate the trig expression. So you're going to isolate sine of x instead of isolating x. Well, that's really not too hard, right? You're going to add 1 and divide by 2, and so you get sine of x equals 1/2. So now, sine of x equals 1/2. There is no algebraic separation of x in this equation, really. What I want you to do is to think about how the unit circle will provide the solutions to this equation. And yeah, if you think about the two places where sine equals 1/2, as you know, on the unit circle, that would be pi over 6 and 5 pi over 6. And there's our solution. X equals pi over 6 and 5 pi over 6. Okay, good. Now, there actually is a little bit more to the story, so let's look at another example. Cosine of x equals negative 1/2. Now, rather than look at the unit circle right away, I want you to, as Bill Nye likes to say, consider the following. All right, look at a graph of cosine x and a graph of y equals negative 1/2. And look and observe that those two graphs intersect each other in a lot of places. And in fact, an infinite number of places. Of course, both curves go on forever in both directions, so they just keep on intersecting each other. And there are literally an infinite number of solutions to that equation. Wow, so how do we express all of those solutions? Well, the unit circle, of course, will give us a couple of them. You can think about the unit circle where cosine equals negative 1/2, and that's at 2 pi thirds and 4 pi thirds. So there's a couple of solutions, but how do we express all of the other ones? We can't just start listing them, that would take forever. So here's how we do this. It's a rather elegant and simple solution to this problem. And so just by way of getting there, let me just remind you that the period of cosine is 2 pi. That means that any points on different cycles of cosine are the corresponding points are separated by that distance of 2 pi. So if you think about that, you'll see that 2 pi to the left of one of those solutions gives me another solution. And 2 pi to the right of that one of those solutions gives me another solution. Starting at either one of the solutions, in fact, I can find another one just by adding or subtracting 2 pi. Well, that's pretty cool, because what that means is then all I have to do is use multiples of 2 pi. So 2 pi times 1, 2 pi times 2, any multiple of 2 pi will give me another solution if I add it to my original there, 2 pi thirds and 4 pi thirds. So the way that turns out for us then, as our expressing the solution, is to just say 2 pi thirds plus 2 pi k, and 4 pi thirds plus 2 pi k, where it is assumed that k is an integer. So that right there solves all the problems. In other words, we are expressing the infinite number of solutions to that equation simply by adding on the little tag plus 2 pi k. Pretty cool, huh? Okay, let's do another example and take a look at some other algebra tricks. Here's an equation that, wow, that looks kind of gnarly, right? Cosine x minus 1/2 times 2 sine x plus square root of 3 equals 0. Wow. Well, first, let me just caution you, do not, in any circumstances, multiply those two things together. It'll just give you a big, ugly mess, and you won't really know where to go. Okay? Take advantage of the fact that it's already in a factored form, and take advantage of the most fantastic property in algebra, well, maybe not the most, but it's pretty fantastic, called the zero product property, which means, of course, that anytime you have a product of two things that equals 0, the only way that happens is if one of those two things, or both of those two things, equals 0. So all we have to do then is consider that each one of those factors equals 0, and we solve those two really simple-looking equations, right? Cosine is equal to 1/2, and sine, a couple of steps there, sine equals negative root 3 over 2, and now we go back to the unit circle, and we get pi over 3 and 5 pi over 3 for that left-hand equation, and we get 4 pi over 3 and 5 pi over 3 for the right-hand equation. So actually there's three different places, three different numbers that solve this equation for us. Let's not forget to add the 2 pi k, and here's my little handy way of doing that. I put the three solutions in a set of braces and add the 2 pi k on the outside, and that covers everything, folks. It's the set of those three numbers, pi over 3, 4 pi over 3, and 5 pi over 3, plus 2 pi k. There's all the solutions possible. Okay, let's do another one. This one is in factored form, but sometimes, unfortunately, you have to do the factoring. So here's another equation, and this one also has this extra wrinkle in there of having two different trigonometric functions in the same equation. And while that's possible to deal with sometimes, generally it would be to your advantage to rewrite the equation in terms of just one trig function. So let me remind you of something very useful. The fundamental Pythagorean identity says that cosine squared x is equal to 1 minus sine squared x. So we're going to use that substitution in place of cosine squared, and then we'll have everything in terms of sine, right? So I replaced the cosine squared with 1 minus sine squared. I'd use the distributive property to multiply out, and now the right-hand side looks like that, 2 minus 2 sine squared x. The zero product property, of course, is very, very useful, so I will subtract that 1 plus sine x from both sides so that I can come up with, set the whole thing equal to 0, and look at that step right there. That's just kind of spreading everything out. Then I can combine some like terms there, and we're almost done. I just don't happen to like having a negative leading coefficient if possible, so I'm going to multiply the equation by -1 and have my final form there as that, 2 sine squared plus sine x minus 1. And all I've done so far is rewrite the equation in this kind of standard form quadratic type of equation. Okay, so now we will solve. Now, that structure there, that equation, is really the same structure as something like 2x squared plus x minus 1. Exactly the same structure, and in fact can be solved with exactly the same technique, namely, in this case, by factoring. So that one does factor, and yes, maybe it's been a while since you factored a quadratic like this, but keep at it, you can get through it. It factors to like this, 2 sine x minus 1 times sine x plus 1. Then we have the zero product property coming in and saying, oh, okay, well that's two really simple equations. Sine equals 1/2, sine equals -1, and so we get pi over 6 and 5 pi over 6 for the first equation. And interestingly, the other equation only has one solution because there's only one place where sine equals -1, and that's at 3 pi over 2, at the very bottom of the unit circle. Okay, so there's our three solutions, and we shall write them all in a set of braces, and then, of course, add 2 pi k, and we are done. Okay, so we had to do a little bit of work to get it into a nice form, but once we got it into that form, it was pretty easy to solve that equation. Let's look at one more example. In this case, reminding you of something else that we've been studying, which is the double angle identities. And there's sine of 2x minus cosine x equals 0. So there you can see that in this equation we've got sine of 2x, and I'm hoping that you're thinking, sine of 2x, that reminds me of something. Oh yeah, that double angle identity for sine. That is what we're going to use here as a substitution here. We'll replace sine of 2x with 2 sine cosine, and now you can see, oh yeah, there's cosine is a common factor for those two things. We're going to factor out cosine, and now we're going to use the zero product property, and bada boom, bada bing, we got our answers there from those two simple equations. And there you go. Again, we put all four answers in a pair of braces and add 2 pi k, and we're done, folks. Okay, so I hope that was good. Please feel free to come back and look at this video or any parts of it as many times as you like. And now, go do some math. Bye-bye.